Hello. So let's start today's talk. We'll just first recap what we have seen in the last talk. So in the last video, we have seen what is a freestanding Rust binary and how to create a Rust binary which is not linked with any of the underlying operating systems. And for that, we have fixed the panic handler issue, that we need a panic handler. We need a starting point, that is we cannot start with main. We need a starting point that is called as underscore start. Then we have seen that we need to take care of the unwinding of the stack in the panic handler. So for the sake of simplicity, we have checked it or we have made it as abort. So whenever the panic happens, we will just abort our program or our execution. And finally, we have fixed the linker errors by defining a target, by defining a cross compiling target. And at last, we were able to generate a binary which is not linked with any underlying operating system. So in today's talk, we are going to see how can we boot up minimal Rust kernel. And so first of all, let's start with the boot process. So what is the boot process is, whenever we first of all start our computer, it basically starts a very basic minimal bootloader which sits in ROM. Now ROM is a read-only memory, and this bootloader is immutable bootloader. That is, once it is flashed into the ROM, we never change that bootloader. So generally, this is also called as a first stage bootloader. Now this bootloader performs a very simple operations. For example, it checks power on self test, and it initializes the RAM. Or first of all, it detects what is the available RAM. It pre-initializes very basic or very minimal required CPUs and hardwares, and afterward it looks for the bootable disk. And once it finds the bootable disk, it starts booting from there. Now till now we have seen many a times we have seen our Windows system starting up with a blue screen that is called a basic input output, that is BIOS. So BIOS is one of our firmware standards, and another is UEFI, that is Unified Extensible Firmware Interface. So we have seen these two of the bootloaders that I would like to say, which we have seen in our general purpose computers. So now when we are creating a kernel, Linux kernel, we need a bootloader also, which boots up our Linux kernel, which takes care of this booting up process and then transfers the control to our designed kernel. So for that, here we are talking about what is the BIOS boot and what is the multi-boot standard. So what the author is saying, that BIOS is a very basic boot which has been there since I think almost 20 years or more than 20 years. So what actually happens in this BIOS booting is, it actually switches your CPU execution mode to a real mode. Now this real mode is nothing but a what we can say, it is a 16-bit mode, and it has it is a high privilege mode. Basically we can do we can this is what we can say, we can do a lot of things which is not meant to be done on a particular controller. For example, we can tweak with your hardware, we can tweak with your some of the peripherals, timers, and all those things. So that's why this execution is called as, it is a real mode, and it is very high privileged mode. And this, in this mode only, I think this BIOS boot only executes in this particular mode. So once it initializes, BIOS boot initializes your hardware by switching to real mode, then it again switches back to the protected mode, that is 32-bit mode, and then if it requires, then it switches back to the 64-bit long mode. So this is what a boot image does, or a bootloader does for us, and BIOS bootloader does for us. But what the author is saying, that if we are not going ahead with BIOS boot, because for BIOS we need to append a extra image header or bootloader image header onto our kernel. So for that purpose, we are going with multi-boot standard. Now this multi-boot standard is nothing but, it is an open source bootloader, or GNU Grub. You must have listened the name of Grub, which takes care of detecting our kernel, and for this we just need to append a multi-boot header on top of our kernel, which can be generated with multi-boot tools as well, which are provided, which are really open source. So we are going to use this multi-boot standard, and this is provided by Free Software Foundation, and it supports only 32-bit protected mode. That means you still have to do the CPU configuration and switch to 64-bit long mode. And so for that we will be using multi-boot standard, which with which we are going to append a multi-boot header in front of our kernel, our generated kernel. And once this whole binary is packed, this binary can be used to boot our actual machine as well, actual hardware as well. But we are going to demonstrate this on a emulator, a QEMU emulator. So let's start with the kernel now. So what the minimal kernel is, here we are saying that it will print an hello world to the screen when booted up. So for that, let's go back to our VS Code instance. Okay, so I think this is visible. Yeah, so this was our freestanding Rust binary which we have created. It just had a starting point and it just goes to an infinite loop. It has some basic implementation of the panic handler and the abort functionality when the panic occurs. Okay, so now let's see what we need to add to this. So first of all, make sure that Rust Nightly is installed. So for my thing, it is already installed. I'll just confirm. So in order to check, I'll just say rust up. So we can see active toolchain on my desktop on my Mac OS is it's already to the latest nightly version, Rust C Nightly. Then what is saying that yeah, for nightly compiler we need to use an ASM macro, and this ASM macro is nothing but it's a feature flag which is not which does not comes up by default. So in order to enable this flag, we need to add this particular string in our main. So we'll add that thing because down the line we will be going to use some inline assembly also. That's why we need this feature to be enabled. Okay, now in the last video you have seen that I have specified the target as thumb v7. So when we compile cargo build release -- target, we have used something like thumb v7 none EABI HF, something like this. In order to be more specific, let's go back to the last discussion, and here we have used this particular target. So if we do this, we get our build finished. So this is how we have built our freestanding Rust binary. But now we don't want to boot the thumb v7, the ARM target. We want to boot x86 64 target, that is our a Linux machine. So in order to that, in order to boot up an x86 machine, we need to define the target. So by default Rust supports multiple targets, so we can see the list of targets as well by using this command rust up. Something was there. Let's go to the command which depends. Okay, now cargo system supports different target architectures, but we want to we want to compile this particular Rust kernel for a very specific target, that is x86 64 unknown Linux GNU. Now this is what this is how we define our target using a target.json file. So this is a specific example of JSON file which is already which should already be available or which is already shipped with the language itself. So what it does, what all things are there included in this particular target is the name of the target, the data layout, it specifies your width of all the integers or all the data types. For example, I64 is 64, I128 is also 64, F80 is 128, I32 is 16, and so on. So this is how we define at the width of our primitive data types. What is the architecture? Then endianness we define, the pointer width we define, then cint width, Linux executable, then linker flavor, and some of the extra things. So this is an example of a target specification JSON file. Now we need to create our own JSON file for our target. So what our target is, you can see it is x86-64, unknown, and none, because we don't have any underlying operating systems. So what the author is saying, that we need to define our own target.json file, and it should look something like this. We will so first of all, let's copy this target dot this contents, and okay, where is my this thing? Okay, and here we will create a new file. Let's create it as x86 64 unknown and none dot JSON, and here we define our JSON contents. Okay, so our target is x86 64 unknown and none. Our data layout is very much similar to what we have seen previously. Architecture is x86 64, target endianness is little endian, pointer width is 64, and rest of the things are very similar to what was there in the example. Now note that we have changed the OS in the LLVM target, and the OS field is set to none. So if we see, I'll go back to our this thing. So OS we have defined none because we ourselves are creating OS. So if we see here, the already existing Linux GNU target, in this flavor the OS was defined as Linux, but in our case we are saying that OS is none because we ourselves are writing an operating system. Then we add following built-in related entries. So what is says that the linker flavor is, let me add these entries also over here. So, and what is the significance of these entries, we will see. It basically says that we need to use cross linker for this, that is cross platform linker that is being shipped with our Rust for linking to our kernel. Panic strategy is abort, so this also we will copy it here. Now if we do a panic abort here, then no need to specify it in the cargo.toml. So either way we can do, we can define it in the cargo.toml, or we can define the panic strategy over here also. Then we are disabling the red zone. So what a red zone is, basically we can go into this thing. Let's go, what is disabling the red zone? So what they are saying, that for each function there is a red zone of 128 bytes below that stack of the function. Now this red zone takes care of any buffer overflow, or whenever if there is any other function which is increasing its stack size, and if that function enters this function's red zone, then it basically throws an error. So all these things are very OS specific. We don't want to we don't want to handle all such cases. So that's why what we are saying, that just disable the red zone. So we have we have what we have done is this, we have just made it true for the sake of simplicity. Then we are also adding some of the features. So what these features are, let's see. mmx minus. So if you see this minus sign in front of mmx, in front of sse, and a plus sign in front of soft float, it indicates that we don't want mmx features, we don't want sse feature, and we want soft float feature. So what is mmx and sse? It determines the support for single instruction multiple data, that is SIMD. Now with this, if we have the support with of this instruction, we can do a lot of operations in a very optimized way. For example, array operations. If I want to do a particular operation on a set of an array or 100 bytes of array, I just want to increment all the element of an array by 1. So I can use this single instruction multiple data support. It is already built into our operating system, but now again, for the sake of simplicity, I am disabling it. And also it is required for our floating point operations. Now then the next question comes up is, how are we going to handle floating point operations? So for that purpose only, we are enabling soft float. Now soft float, what it does your floating point operations in a software way without using the hardware single instruction multiple hardware instructions. Basically it wraps up a software function which basically uses your integer data type to do a floating point operations also. So that's about that's about our target specification. Now since our target is ready, let's build this target. So in order to build this, what we have to do is cargo build, and in this way we can define our target, so which target to be used. So now here they have used block.json. Now here we have to provide our own unknown none.json, and if we do unexpected argument build found, so what it says that oh no, we don't want rust up, we just want to build cargo. So this is the command for us, and it is saying that can't find crate for core. That is the expected error that these guys are also mentioning over here, that they don't find a crate for core. Now if you understand this correctly, so our Rust comes up with a standard library and a core library. So we were using the core library in our assembly file or in our binary file, but this core library is also compiled for a specific architecture. It is not compiled for user defined architecture. Now since this architecture which we have defined is our own architecture, we need to build this core library for our own architecture also. So how to do that? They are saying that we can do that by using this two by adding these two lines in our config.toml. So what they are saying, the problem is that core library distributed together with the Rust compiler as a pre-compiled library. So it is only valid for supported host triplets, not for a customized host standard. So in order to build the core library for our customized or custom target, we need to define a config.toml file, and this will go into our config.toml file, which says that while building our crate, we need to build core library also and compiler built-in also. Now what is compiler built-ins, we will see, but before that let me add this to our config.toml file. So for that we will create I will create a folder over here which says .cargo, and inside this we are going to add a file name as config.toml, and here we will paste this particular line which says that while building our binary, you please build the core library and compiler built-ins also for that. And now if we see, now recompiles the core and Rust standard workspace. Okay, now let's again build it. So you can see it is compiling the core library also. core version 0.0.0. Now it is finished. And is our binary ready? No, we still need to add the hello world for hello world to be printed to our screen. So how to do that? First of all, let's see about memory related intrinsics. So what this memory related intrinsics are, it basically are some of the inbuilt functionalities which are there in our operating systems. For example, okay, let me plug in a power source quickly, otherwise battery will drain out. So okay, okay, so my laptop is happy and I am also happy. So what are memory related intrinsics are? These are compiler built-ins that are used. For example, some of the compiler built-ins are memcpy, memcompare, memset. Now these are all defined in our C compiler, and in order to get this compiler built-ins for our architecture, we need to compile this particular built-ins also for our target architecture. So for that, we need to add one more line, that is compiler standard feature or build standard features. So which says compiler built-in and memory related intrinsics. So if we add this line also, it will build these compiler related built-in intrinsics also for our memory. Now yes, now our binary is ready. And so another way, so here what they are talking is, another way is we can ourselves implement memcpy, memset and memcmp, but that would be really tedious, and even a slightest error while implementing that can lead to can lead to errors which are very hard to debug. So that's why we just enable this feature from the compiler, and the compiler will build this memory related intrinsics for us. Now here it is saying how to set a default target. So that thing we have already done. Every time we don't need to specify the target, we'll just add this line into our config.toml. So this is our config.toml. So here we can specify target x86 blogos.json, but here our name is this one. So I'll just copy the name, Control C, and go here and paste it here. So now if I want to build, I can just say cargo build -release, and it will build for my custom architecture. Yes, it's built. Now let's go and add support for printing to the screen. So what we are using a VGA text buffer. They are saying that it's a special memory area mapped to the VGA hardware, and it contains some 80 character cells into 25 lines. And for printing hello world, we need a static string and the start address of our VGA buffer. So VGA start address buffer is this thing what they have mentioned for x86 64 targets architecture. So let's start with the code. What they are saying, we are, so let's write it over here in the main function. This is our start function. Let's define a static string which is hello, and it says hello world from Rust OS. It needs to be character of UID, so it has to be we cannot use vex, so it has to be a static array. It is a reference of U8. Reference of U8. I think this not as bytes. This is fine, or we can add a b also in front of it, doesn't matter. So into our start function, what are we doing over here is we are just writing byte by byte from this particular string to a VGA buffer. So let's do that. let VGA buffer is equals to VGA buff equals to 0 cross B800, and for I comma v in hello dot iter dot enumerate. Because we are enumerating, we need an I and the value for it. And what are we doing is we are just writing VGA buffer offset I as use size, and it is equals to byte. So what we are doing is we are dereferencing a VGA buffer at an offset of I, and that is equals to byte. Okay, first of all, this is as reference pointer, mutable reference to U8. So this is our pointer, and finally we write some unsafe code over here. So what we say is VGA buff dot offset of I is equals to V, pointer to V. Into 2. This is what we are. I as I size is equals to byte. Okay. I as I z. Okay, because offset needs to have an argument of I size, and then we need to increment the offset also. So VGA buff dot offset I as I size into 1. Is equals to 0 cross 0 B into 2 plus 1. I think here we are writing 0 cross 0 B. Okay, let's do it what it is being done over there. Plus 1 equals to 0 cross 0 B, or 0 cross B only. So let's see what 0 cross B defines over here is it has 24 line. Each character cell displays an ASCII character with some foreground and background colors. Screen output looks like this. So VGA buffer is like this. It is a raw pointer and iterate over a static byte. We use enumerate method. Okay, so this is a color which we are adding. So that's why in the body of the for loop we use offset method to write string byte and corresponding color byte 0 cross B. It's a light cyan color. So that's why we are using 0B, and I want to emphasize that this is not the way we want to do things in Rust. It is very easy to mess up with working. And yeah, it is here the author is talking about the unsafe things. We don't want to use unsafe block anymore. This is just because we are starting and we are just on the stage of an hello world. That's why we are using unsafe, but this is not how the things are being done in Rust world. So let's get this thing compiled. I think our hello world is also ready. Let's do a cargo build -r. Yes, it's compiled. And finally, to boot it, we need to create a boot image for it. First of all, we need a QE emulator in order to test our kernel image. And in order to test our kernel image, remember I have talked about a multi-boot standard which we were using. So that can be done with this particular create boot image, and we have to use a specific version of boot image 0.9 only. So let's go ahead and add that dependency over here. Let's see, boot image is equals to 0.9. We need to install it also. So let's do cargo install boot image. So this is going to install boot image for us, and this boot image will going to take care of the thing which we have talked previously, that it is going to append a boot image header on top of our kernel, so that the multi-boot standard which we were using to boot our emulator, that will recognize our kernel and it will boot our kernel. So yeah, so this this boot image is also installed. Now let's go ahead, and what we need to do, we just need to add LLVM tools preview is already added, I think so. So we just need to add cargo. We just need to run cargo boot image. So cargo boot image. Let's see what is happening. Building a kernel. Okay, there are lots of errors. Okay. Okay, kernel build failed. I think we have messed up with some of the data types. We just okay,